Given videos such as the one on the left, the goal of this work is to estimate the 3D camera rotation from an optical flow field between two consecutive frames. Let's first consider a pure rotation flow. Note that pure rotation flows are independent of the scene geometry. Let's take a single optical flow vector u, v, at location xy. We want to find the set of all camera rotations that could have generated this flow vector. An optical flow vector has two free parameters, and the space of rotations is 3D. Therefore, there is a 1D manifold of compatible rotations. On the left, this is the visualization of an optical flow field. On the right, this is the rotation space. The optical flow vector at the location of the blue dot is compatible with the 1D manifold of rotations in the rotation space. Since we are in the pure rotation case, we can retrieve the rotation that has generated this flow field with only two flow vectors. The rotation is given by the intersection of the two manifolds. In the pure rotation case, all the 1D manifolds of compatible rotations intersect in a single point. However, in real-world videos there are other factors that affect the flow in addition to rotations. There are also translations, moving objects and noise from the flow estimation. However, the effect of translation on the points is inversely proportional to their depth. Therefore, the effect of translation on points that are far enough away can be ignored. Let's now consider a real-world flow. If we sample flow vectors that are on static faraway objects, then their manifolds of compatible rotations come close to intersecting in a single rotation. On the other hand, the manifold of rotations generated by the flow vectors that are either on close by objects or moving objects do not give coherent rotation estimates. Therefore, by adopting a voting scheme on the rotation space, we can robustly estimate the camera rotation. On the left, the red vectors show optical flows compatible, with the winning rotation estimate indicating the rotation of the camera. Gray vectors show optical flows not explained purely by the winning rotation. On the right, this is the rotation space. The red lines, corresponding to the red flow vectors on the left, intersect in a single small bin, indicating that their optical flows are compatible with the same rotation. The gray lines, which are affected by other motion effects, are scattered in an unstructured manner, and correspond to the gray optical flows on the left. Our algorithm finds a set of lines with greatest coherence in SO3, revealing the rotation of the camera. Now we describe two methods to get the set of compatible rotations. The first one uses perspective projection. In brief, we want to find all rotations that rotate the vector OP onto the vector OQ. This can be done by composing two rotations. The first one is a unique rotation about the cross product of OP and OQ. This first rotation aligns OP and OQ. Now, any arbitrary rotations about OQ will keep OP and OQ aligned, and therefore they generate the set of compatible rotations. The second method is an approximation using the Langevin-Higgins motion model. The system of equations defines a line in the rotation space. Note that the slope of the line is independent of the flow vector. For small angles, the lines of compatible rotation given by the Langevin-Higgins motion model are good approximations of the real 1D manifolds of compatible rotations. The Langevin-Higgins motion model-based method is significantly faster while maintaining the same level of accuracy as the method based on perspective projection. In order to evaluate our proposed algorithm in the context of crowded scenes, we introduce a new dataset called Busy Street Scenes, or BUS. This dataset is composed of 17 HD video sequences. The videos are taken from a handheld mobile phone in crowded city streets with synchronized gyroscope data. All faces in the videos have been blurred. We compare our proposed method on the BUS dataset with other methods using RenSAC. We show that our method is more than 50% more accurate for similar runtime. We also evaluate our method on the IRS-TV sequence, which is a sequence taken from a handheld camera but with few moving objects. As expected, in the absence of moving objects, our robust method has similar performance to other top methods. We can qualitatively evaluate our results by using our rotation estimates to stabilize videos. The video you are currently watching is the original video from the BUS dataset. Now this is the same video but stabilized using the rotation estimates from our algorithm. As you can see, the faraway points are stable. This means that the rotation has been correctly removed. In conclusion, we presented a novel robust method to estimate the 3D rotation of a camera. Among comparably fast methods, our method reduces error by almost 50% over the next best, and is more accurate than any method irrespective of speed. In addition, we introduced the new BUS dataset that consists of 17 video sequences in crowded, real-world scenes.